1, 2, 3, yep. So just before we start this session, which to my horror I see is the longest session of the whole meeting, but anyway, I'm Jeremy Pearson from London, you'll hear from me later. I just wanted to ask, what fraction of you are basic scientists doing a PhD and are not clinicians? Stick your hands up. And which are the others? In other words, clinically qualified or qualifying as clinicians and doing basic science? A minority. Okay, that's worth knowing. Thank you. So we've got this session on effectively career development in various ways. And to start off, Dirk Duncker is going to tell us about designing your experiments properly. Dirk.
Jerry, thank you very much. It gives me great pleasure on the one hand to be here. At the same time, you can tell from the subtitle that I feel a little bit uncomfortable telling people how to design their studies because there is, there's all these issues that when you're designing a study that halfway through the study you'd like to change it a little bit. How can I use the pointer? Is this? Is this the pointer?
Screen, I think.
Oh, it's on the... Oh, yeah? Okay, I do it like this. Okay. And so, but let me give you a bit of an update or talk about particularly experimental design and to a lesser extent about statistical analysis. I'm not a statistician. I'm not a methodologist. I'm an experimental researcher like yourself, and we've also been struggling sometimes with doing the analysis properly and setting things up properly. And the first time I gave this talk, at that time I was actually, as I still am today, but then even more, I was involved in cardiovascular research, first as an associate editor and then as a deputy editor. I'm currently an editorial board member, so I will also give you some perspective of cardiovascular research, although the editor-in-chief himself is here, the current editor-in-chief, Tom Guzik, and he can correct me if I'm wrong, but I got this from the website. And so I think it's important to realize that if you're publishing basic science, and our flagship journal for the Council on Basic Cardiovascular Science is cardiovascular research. It's important to realize that it's intended for basic and translational research spanning all topics within cardiology and cardiovascular biology. And that we publish papers at the molecular, subcellular, cellular, organ and organism level and clinical proof of concept and translational studies. All these studies are aimed to enhance insight in cardiovascular disease mechanisms, and that's a term, mechanisms is a very important term in many of the more basic journals, and also the perspective for innovation, because it's a European Society Cardiology journal, cardiovascular research, so the perspective for innovation and also translation to the clinic is very important. And it should provide a significant contribution to the field with relevance for cardiovascular biology and diseases. So not just biology, but particularly also diseases. Now, of course, any study starts with a great idea, and you made an observation, you read the literature, and you say, I got this idea for an experiment. So that's where it all starts. But what is what's the importance of a study design? Well, the design is actually something that of the study is the structure of any scientific work, and it gives direction and it systemizes your research. And so it is the framework that is created to seek answers to your research question that you've just posed, and that your supervisor says, I think that's a great idea, you should do that. Well, there's a variety of designs. I will not discuss all of them. There are descriptive designs, correlational studies, semi-experimental designs. What I understand is that then it's almost like an experimental study, but there's no randomization. That can be difficult, for example, with clinical studies. Reviewing, systematic reviews. That is also becoming more important for preclinical studies, and there's meta-analyses. But I would like to focus on experimental studies. Now, you can do that in the lab. You can do it in the field, but I'll show you some examples of laboratory-related experimental studies. Now, the experiment. An experiment. What is an experiment? It's a procedure carried out to verify, refute, or validate a hypothesis that you've formulated. It provides insight into cause and effect, particularly in basic science. I think we find it very important because that tells you something about also mechanisms. And by demonstrating what outcome occurs when a particular factor is manipulated. So what you would like to do if you think this factor A is really important for, let's say, atherosclerosis, what you want to do is keep everything constant and only change this one particular factor and see how it influences the process of atherosclerosis. Now, experiments can vary greatly in goal and skill, but they always rely on repeatable procedure. And that's not easy these days when many journals also want you to have a very brief methodological section. And sometimes, it's only in the online version, but at least there it can be expanded. I think it's very important because many times you read a paper, you cannot repeat the experiments that they did. And you have to contact them through email. They say, well, that postdoc left our lab. And we basically don't have much of an idea of how to do this. So you cannot repeat somebody else's study all that easily. And I think that's a continuing point of concern. And so I personally think that it's very good that there's these online supplements where you can put all that data in a lot of detail. And it also relies on logical analysis of the results. Well, we all know that from when we're young, we can do all sorts of experiments. In this particular case, this child is seeing himself in the mirror, and I think this is something that the apes, and I think some monkeys, they recognize themselves as being, hey, that's me. Many monkeys don't, and they keep attacking the mirror. But so there may not be a logical analysis of the results, but in this particular case, the children can at least make it a repeatable procedure. They love to do it again, do it again, do it again. Not sure if this child will have a logical analysis of the results, but at least this is something that I think is also in human nature, and I think to perform experiments. So these are some aspects of an experimental design that I would like to go through with you and give you some examples of that. And some of the things that we've also been struggling with. So you can first have to ask yourself, how many factors does the design have? Are these factors, and these are the factors that you control, are these fixed or variable? You can also call them independent factors. And then you study the dependent factor. In my previous example, when you change factor A, then factor A is a factor. And then the atherosclerosis is the dependent variable that you are studying. So are these factors fixed or variable? And what is the relevance of interactions between these factors? Well, this is an example of studies that we did, and I'll show you particular examples from cardiovascular research. This is a kind of experiment that we actually based on observations from Professor Heusch and Schultz in Essen, that depending on the type of preconditioning stimulus, different mediators are involved. Because at that time there was a big discussion about adenosine. Jim Downey had discovered that adenosine was involved in ischemic preconditioning. But people said they're important in all species, but not in the rats. And people had performed these kinds of studies. And what they did is they had performed here, this is like a 60-minute coronary artery occlusion. You see that here, for example, and that produces an infarct size of 70% of the area at risk. And if they did a 3 times 3 minute ischemic preconditioning stimulus, they could markedly reduce the infarct size as compared to the corresponding control. But if they blocked the adenosine receptors, there was no effect at all. And so we performed a study more sort of analogous to the studies that Professor Heusch did in the pigs, showing that if you have an extended preconditioning stimulus, that adenosine might be released and could contribute. And indeed, this protection by a single 50-minute coronary artery occlusion did not result in as much protection as the triple 3-minute preconditioning stimulus, but it was very susceptible to inhibition by the adenosine receptor antagonist, the sulfophenyltheophylline. Now, here first, one of the things you can think of is first, so how do you design the study? So what kind of protocol do you use? You need your proper Shem groups showing that the adenosine receptor antagonist itself had no effect, because if this would have been the effect of the adenosine receptor antagonist, you would have said adenosine is protective against myocardial infarction, but it has nothing to do with the protection by the preconditioning stimulus. But the fact that it has no effect, no significant effect, and it does block the preconditioning effect, clearly implicates adenosine in preconditioning and not so much in basal myocardial infarction protection. So that's one aspect. The other aspect is here, so how would you now do the statistical testing? In the old days, and I'd say 50 years ago, people would just do t-testing. These are actually 6 groups that are not related, so they are, let's see, no, that doesn't work. I don't like this pointer here on the screen, but okay. So they're not related, so people would just do unpaired t-testing, indicating that these groups of animals are not, so each animal is a data point, they're not related to one another. But the proper way to do it, if you analyze how the study was actually set up, is that we have 3 interventions. That's a sham, so that's only the coronary artery occlusion of 60 minutes. We have preconditioning with 15 minutes or preconditioning with triple 3 minutes. And then those 3 groups, we do it under control conditions, and we do it in the presence of sulfaphenylthiophylline, the adenosine receptor antagonist. So factor 1 is the preconditioning stimulus, and factor 2 is the adenosine receptor blockade. So this is a 2x3 factorial design. And so what we actually did some 20 years ago, we just performed a one-way ANOVA. I just checked it last night, and I thought, I would have done that differently today, because what you do with the analysis of variance is making sure that, for example, this effect is not a coincidence, and that you have the variability within all the experimental groups taken into account. That's why you do analysis of variance for all 6 groups. But a one-way ANOVA is not as good as a two-way ANOVA, where you really take into account the effects of the adenosine receptor blockade in relation to the preconditioning stimuli, and you can also look at the interaction. So that's the way it should actually be analyzed. So two-way ANOVA should be the proper way of analyzing the data. Another example of factorial design are studies that we are doing in chronically instrumented pigs. We do surgery on the heart. We have these animals recover, and 1 week later they run on the treadmill, and they run, first they're lying, and when they're standing a little more active, and then they run up to 5 kilometers per hour. Doesn't seem like a high speed, but with the short legs, they go up to 85% of maximum heart rate. These are 25 kilogram pigs. These days we have 100 kilogram pigs on the treadmill, and that is no joke. If they are not amused, they're big animals, but these animals run up to 85% of their maximum heart rate. At least these were the studies that we did some 20 years ago in these animals. And so here, having 7 levels of physical activity, you can see that here the factorial design is a 2x7 design. We have control and nitrile arginine and 7 levels of physical activity. So this is a 2x7 design, and here you would have to perform a two-way ANOVA as well. What you can also do is, rather than saying I use the fixed exercise levels, you can say, well, I want to study some of these variables. This is coronary vascular conductance, it's the inverse of resistance, or this is the coronary venous oxygen tension, and I want to study it as a function of myocardial oxygen consumption, because studying the coronary flow or the coronary resistance vessel tone is not so relevant to have the absolute level of exercise. It's much more relevant to relate it to the oxygen consumption state of the heart, because that will dictate how much flow will be needed. So here you can apply a different type of analysis. It's still a 2x7 design, but rather than calling it a two-way ANOVA, this is an ANCOVA, analysis of covariance, where you actually have a variable factor, myocardial oxygen consumption, and you relate the difference between the control and the NLA, the nitro-L-arginine, an inhibitor of NO synthase. You correlate that to the level of myocardial oxygen consumption. And you can appreciate that for this particular factor, it does seem like there's also an interaction, so the effect is greater at higher levels of oxygen consumption, whereas for the coronary venous oxygen tension, it seems to be constant over a whole range of myocardial oxygen consumptions. So I've shown you here a control group, or a control run exercise, and then having an exercise run in the presence of nitro-L-arginine. And so why do I readdress the control conditions? Well, they are certainly needed. You need to have the proper controls. Like when you do Western blotting, you need positive controls, you need negative controls. And also in this exercise study you need it. You can say, well, you had a control run and then a nitro-L-arginine run. And that is true. But what you also need to know, these effects that we ascribe to nitro-L-arginine could have been simply the result of having a second exercise run on that day. The animals could have been adapted, there could have been some sort of conditioning effect so that they would have much lower heart rate responses that we now ascribe to a nitro-L-arginine. And so the proper control in this particular case is do a study where you have 2 consecutive control runs. And indeed, if you look carefully, you see that there's a trend for, not statistically significantly, but there's a trend for lower heart rates during the second control run as compared to the first control run. And so if you properly want to compare the effects or study the effects of nitro-L-arginine here, you need to do actually a 3-way ANOVA, where not only do you look at the Shem versus nitro-L-arginine, the 7 levels of physical activity, but also take into account the effects of a second run versus a first run. In most studies, including in our study at that time, what we basically did is said, oh, there's no significant effects in the control group, and that's what I think a lot of people will do, but there is a significant effect in the nitro-L-arginine run, so we left it at that, and reviewers were fine, and I think the differences are so large that we probably are okay. But the real proper, very strict way should be to do a 3-way analysis of variance that will result in probably a requirement of larger groups of animals. And these days, and I'll come down to the later on, come back to the group sizes. If we apply with our ethics committee for larger groups, because we want to look into doing the statistics like this, we get advice to do the statistics differently so that we need fewer animals. So it's not always being strict. I'm Dutch, so we have many Calvinists in the country, so it's good to be very strict and tough. But sometimes you have to be maybe a little bit more Catholic. I don't know if I'm insulting anybody, but I'm Catholic myself, so I think I can say that. So you have to take into account the circumstances and the available resources. But in any event, I think if you look at this, these are the 2 control runs here compared to do the nitro-L-arginine run, and here it goes same for the coronary venous conductance or coronary vascular conductance. You see that these effects of nitro-L-arginine are much larger and there's a good reproducibility of these control runs. So we were happy with this. But in fact, this way we should have probably analyzed it according to some statisticians, is that here we have factor 1, the nitro-L-arginine versus the Shem. Factor 3 was the first and the second run, and now we have, instead of having the exercise levels, we have the covariant, which was factor 2 at the exercise level, covariant myocardial oxygen consumption here. So you do then a ANOVA with 2 fixed factors and 1 covariant factor. Okay, maybe a little bit boring. We can always talk about this later on and discuss. So how far do you need to go? But let's say you also need to test your intervention tools, because I would have expected a question from you saying, how do you know that nitro-L-arginine is doing what it's supposed to do? Well, we also tested that in that particular study, and this is ATP. Typically, you like to use acetylcholine, for example, but in the pigs, it's not as good as an endothelium-dependent vasodilator as it is in dogs or in humans. So we use ATP, and you see that the effects are blunted by nitro-L-arginine. ATP may, at higher dosages, also act through adenosine, and that may explain why the systemic vascular conductance is increasing. But there was absolutely no effect on nitroprusside, which is like ATP NO-dependent, but not eNOS-dependent. So this is a direct effect of NO on the vascular wall, and this was not affected by nitro-L-arginine, whereas the ATP effects were blunted. So we were happy with the tool that we were using. Another question is that when you're doing experiments, you need to take background variables into account. There are confounding influences, and particularly as reviewed in a review paper in cardiovascular research a couple of years ago, and again I think reviewed in other papers more recently, looking at myocardial infarction and looking at cardioprotection, as Professor Hoysch will also probably discuss on Wednesday, is that there's many determinants of myocardial infarct size that you need to take into account when you want to study an intervention. And for example, the ischemia time. You will say, duh, and you occlude the vessel and you reperfuse, and in the lab you can control that very well. Clinically, the ischemia time is not very well defined, if not at all. It's based on symptoms, but that's very unreliable, and you don't also know the severity of the occlusion. Is it total, is it partial, and so forth. So ischemia time is extremely important, and in experimental studies, fortunately, that is always maintained constant. The area at risk is another one. You can look at the infarct, but was the area at risk very large, and did you have a relatively small infarct, or was 90% of the small area at risk infarcted, which in fact is a large infarct of that particularly jeopardized territory. So important to determine it. You cannot publish your results if you do not determine area at risk in experimental studies these days, for a number of years already. Collateral blood flow, very important in collateral species like the dog or baboon. You need to measure collateral blood flow and express infarct data as a function of the collateral flow. Temperature is very important. You need to maintain it in a very small range because it can clearly affect the infarct size. Hemodynamics, there's some discussion about it, but it's very good to maintain it as constant as possible. And more recently also there's a lot of discussion also about, for example, genetic background. For example, you have the C57 black 6, J mice or N mice. Christopher Maak has done a lot of studies on that. Having different enzymes, I think, also in the metabolic pathways, resulting in potentially different infarct sizes. So very important to specify exactly what the strain is that you're using. And also risk factors, and I will not say a lot more about that because I think Professor Schultz is going to talk about that on Wednesday morning. But that clearly also can very much influence the efficacy of therapies that you're studying. And in fact, it's good to include them, but you have to know which ones they are and how to apply them. But definitely very important because that makes your model more translatable to the human situation. So we talked about sample size. Very difficult, I think, because we've asked our ethics committee that we wanted to do 16, no, what is it? Actually 20 mice per group, 10 males, 10 females. And they said, why don't you start with 5 versus 5? If there's no difference, you put them together, you're done. And we can cut the number of mice, into 2 or by 2. And then we said, well, we're interested in finding this out. And they said, yeah, but, 5 animals can still tell you whether there's a trend or not. You get a false negative result because you say, oh, it's not statistically significant, so we can group them. But in fact, I think this is not the right way to go. Barbara Cassaday, a couple of years ago, gave a presentation. If you, after 5 versus 5, do an interim analysis, you determine the p-value, it's 0.07, and you say, oh, we do a few more animals in both groups, and maybe we'll reach p-value of 0.05. In fact, the next time, the threshold should not be at 0.05, but at 0.025. Every time that you look at this, because you start shopping for a p-value below 0.05. And there's one story that my mentor Peter Verdouw would tell me, and I haven't been able to find that paper, but these were studies in mini pigs where they looked at atherosclerosis, and they started with, I think, 8 pigs in each group. And then they looked whether there were significant differences from a diet or some treatment. And then after 8 animals, there was a trend. And then they went to 12, and then it reached significance. And then they continued to 16 animals in each group. And the significance was gone. And at 20 animals per group, it was still gone. And so they said, normally, people would like to find something. So they go from 8 to 12. They say, yes, it's significant. And they stop the study, and they publish it. They say, look, 12 animals per group, that's a lot of animals. But the way you do it, so you need to, before you start the study, you need to determine how relevant is my finding going to be? And I think it should be, if it's a big effect, I should be able to demonstrate it in 10 animals per group or larger, and depending also on your knowledge of the most important endpoint and variable you have, and how much is the variability in the measurement, and how much large is the data. You have your power analysis, of course, but you cannot, after you've done that, we all do it, but you have to beforehand decide, okay, I will do so many animals and it's defendable because of this. And then you have to also stick to that. And if you want to expand, you have to adjust the p-value and describe it properly. And I don't think many people do that. So technical replicates, that's the final point I wanted to make, versus independent biological repeats. And that's a point, particularly when people are working with cell culturing, for example, and they have a source of cells, and they work from that. And it was described several years ago in the EMBO reports. If you do, for example, an ELISA, and you do something in Duplo or in Triplo, and then what you normally do is you average the 3 observations. Say the endothelin level with this ELISA was this level in this animal, and I had the sample, measured it 3 times. That's technical replication. You look at technical variability of your measurement, and that's perfectly fine. But your large N is 1. But what happens sometimes here, you get a bone marrow suspension, and you have 3 Petri dishes, and you start performing your experiments. This is 3 small n, the small n equals 3. But the large N, it is in fact 1 experimental unit that you're studying, and not 3 experimental units. And so it's very good to do the technical replicate. So in fact, this is large N equals 1, large N equals 2, large N equals 3. So you have here 3, and you need to take those averages before you do statistics. And of course, this is a wonderful way of showing it, is that instead of saying this is N equals 3, it's very good to show the technical replicates. But here you see that too. And this is the way, this is actually large N equals 3. So when you do your statistics, you have to average per animal the observation. That is the, let's say, the strict way of doing your statistics. And in many of the papers that I've reviewed, also for cardiovascular research and other journals, it's not clear at all. Sometimes people say, for this table, N is 3-12. And you have no idea where it's, probably most animal numbers will be N is 3 or 4, and there's maybe 1 or 2 that's 12, and then you use it like this. You have no idea. So the best thing to do is plot individual data. And I'm showing this example from the paper that we published in Cardiovascular Research last year. Initially, we also had bar graphs because they look kind of tight. You see here the averages with the standard error, here too. But in between, we now always plot the individual data. So people can look at it, they can get the numbers maybe from the graph and redo some analysis. So I think it's good that we start plotting these individual data, even though aesthetically, I sometimes like the figures much less than in the old days where we had the bar graph. But people can count and they can determine the number of animals themselves. So presentation of individual data is also something I think that's important. This is one final slide that I want to show, because whenever we do experiments and we say p-value smaller than 0.05, it means that there's a 5% chance that it was accidental. But still, but some people say, for example, Ioannidis, he suggests that we should lower it to 0.005, and or he suggests lower it. He said maybe abandon p-values and use the exact p-value. I think that's also very good, because then people can interpret how significant or non-significant something is. Abandon p-values entirely. I know some physics professors at the Technical University in Delft are doing that. They said, I don't need statistics because I do. But in physics, I think it's much more predictable. Like Kennedy said, within 10 years, in 62, within 10 years we have a man on the moon. And that was the law of physics that were applied, and it worked. And then Nixon said in 71, within 10 years, America will have gotten rid of cancer. Well, we are now, I think, almost 50 years later, and it's still not solved. So biological systems are much more difficult, and I think you probably will need to use p-values. But I think this is an interesting paper to read it and see if we need to change statistics in any way. So again, this is the overview of the scope of cardiovascular research. I will not read this to you again, but I think based on this, I think if you want to enhance impact, and this is where I lead in our editor-in-chief, is that for journals with publishing experimental studies, you like to have multi-layered studies if you want to increase impact. You want to use multiple species, preferably. Include also some human samples, so that what you're observing in your animal work is at least to some degree replicated, or there's if you're studying a protein that's not present in humans but only in mice or pigs, immediately the question is, so how relevant is this? So use multiple platforms. You can use in silico, in vitro, and in vivo, multiple technologies, also multiple lines of evidence of causality, and very important, I think, also for a basic science journal of the European Society of Cardiology is not only healthy but also diseased states. And the experimental design involves, that's important to realize, because now I'm sort of preaching and saying how we should do it, and I know I've sinned a lot in the past, so I will not cast any stone to anyone. But experimental design involves not only the selection of suitable predictors and outcomes, but planning the delivery of the experiment under statistically optimal conditions, so you have to think of that. But I think this is very important, given the constraints of available resources or willingness of animal ethics committees, because they often have a statistically very different view on the experiments that we are doing. And so in conclusion, proper design is, I think, extremely important. Get your control conditions right, use the correct intervention tools, correct for background variables, taking them into account, think about your sample size, technical replicates versus biological repeats, so the real biological variability versus the technical replication of the assessment. And to enhance your impact, multi-level approach is I think, also very important for basic science journals. And all of this, again, within the constraints of available resources. And with that, I thank you for your attention.
Thank you very much, Dirk. Question already at the back there. Find the microphone. And thank you for sticking to time. We have time for questions, so go for it.
Okay, so me and my colleagues always have a doubt whether with small n's, so for example 3 or 5, we can use parametric tests like t-test, or with n so small, we should use non-parametric tests like Mann-Whitney, or if we do the normality test and it's okay, we can use t-test. So we were searching some papers whether we can use it or not, and also not all the statisticians agree on this subject. So can you give me your opinion on that?
Well, you're right. Statisticians do not all agree on what the best approach is. I think it's very difficult to do a normality test if you have n equals 3. I mean, how are you going to determine whether the variables are distributed normally? So usually, I think then you have to resort to non-parametric testing. But my professor of pharmacology, that was my PhD advisor, he had this. He had written his own program to analyze the microsphere data on regional blood flow measurements, and if you had fewer than 6 animals in a group, the program didn't run. He said, I'm not going to talk to anyone before we have n equals 6. And of course, you can say sometimes you do, a couple of verification experiments that are not the core part of the core message, and then you can do fewer animals. But I cannot say, well, you can never do a t-test if you have n equals 3. But I think it's difficult. And your remark about statisticians, I discussed a lot when I worked in Minnesota with Tom Rector, who was the statistician that worked on the VHEFT clinical trials with Jay Cohn and Gary Francis. And I did an ischemia reperfusion study on the importance of temperature for infarct size in the pigs. And I thought it was beautiful. I had many time points all analyzed from the strip chart recordings. And I went to him and I said, I do an ANOVA, but it's killing me, particularly the Bonferroni. And then he said, well, why do you want to present all these time points? You do baseline, end of occlusion, 5 minutes reperfusion, end of reperfusion. You have 4. And then all of a sudden, all the data points became significant. And I said, how can this be? It's the same data points. He said, yeah, but you're saying something about fewer data points. So the chances of having a false positive finding are smaller. And then I thought statistics is a trick. It's not telling me the truth. It's a trick, or it's a tool. And so whenever you use it, that's why I like it if people describe carefully what they do. If you submit your spreadsheets with the raw data sets and you describe the exact test that you did with what program, in principle everybody could repeat it. And I think we don't do it. We often shield it, or it's a lot of work. I also realize that. But I think describing it properly so that people can interpret it and draw conclusions for themselves. If you have a p-value of 0.08, people can say if with 92% chance that it's true, with that sort of chances, we go to the casino right now and become filthily rich. So we're very happy with a 92% chance to win in the casino. But in statistics with our experiments, we're disappointed because we did not reach statistical significance. And I think it's a continuum. It's not an absolute value. But I can't say if n equals 3, I would say go to n equals 6. That would be my honest advice.
And from what you said earlier, start off by saying n will equal 6, not I will do 3 and then do 3 more.
Yeah.
So, for example, if you see a paper in which you have a series of different conditions of experiment in which the n numbers vary from 3 to 15 in different groups, do you ask why? Do you throw it out? Do you know?
Well, it depends. If people say we started out like this, and then based on these observations we continued, and we did these additional experiments, then you can say this is your core observation. That needs to be solid. And then for the subsequent, you can say, well, then we explored, and then you use smaller group numbers. But even then, normally you would have to say, I start the second series of experiments. I also want to have n equals so much. But I think, for example, with the ATP and the nitroprusside data that I showed, there you're testing up to very high dosages. So very often n is 4 is enough to really see if a blocker works. But in biological processes, the effects are usually much smaller, and I think you need larger numbers of observations to draw meaningful conclusions.
More questions? Yep, one over there. Can you grab the mic or somebody hand it across? Thank you.
Thank you. So I have a question about analysis. So if you increase the number of your animals, for example, then you should lower your p-value. But this is also true for analysis. So normally, when we do a mouse experiment, we start with, for example, counting number of vessels in damaged tissue, and then at some point there is no significantly different effect. So then we think, well, maybe we only should count the smaller vessels, and then, or maybe only the larger vessels, or the area of smooth muscle actin, or anything like that. So then you increase your number of analysis. Should you also,
Yeah. In a way, it's shopping. If you do that in clinical trials, you have to say, this is my primary endpoint, that's a secondary endpoint. And in subsequent papers, I mean, there have been beautiful negative trials or positive trials where there were all sorts of spin-off analyses. But as long as you describe it, you say, we first started off doing this analysis, and we found a trend but no significant effect. So we wondered if a particular vessel size would show a significant effect or not. Then I'm sure everybody will say, that's logical. In clinical trials, you say, no, you're fudging. That's not right. But in basic science, you say, that's a smart idea. So why don't you follow that up? And then I think statistically the best thing would do another group and then start off with stratifying. But if you tell that to your supervisor or you tell that to the funders, that, well, you should have thought of it before, or, so we typically do that, I think, as basic scientists, because we're generating ideas. It's exploratory research. But the thing is, you have to describe it, I think. And way too often people present it like they had the idea up front and this was very smart. But I think you got to be more honest. And I think that, Gert, there was this one book, I think Wolfgang, and I'm not sure if you wrote a chapter in it, but with John Ross and Wolfgang Schaper, and they described the career, for example, with the collateral flow, or John Ross with the exercise studies, and they described honestly how it really went, the story. So they said, of course, and then we said this and that. But in fact, we had this observation, we had no clue, and then we performed these studies. And it's extremely insightful to hear that, and I think we should maybe have a little bit more of that in our papers, that we say how we get there.
Yeah, so is this, and also the part about the replicates, the technical and biological replicates, is this part of the guidelines of journals? Do you know that, or should it be in the guidelines?
Yep. I think the editor-in-chief of cardiovascular research will also allude to that, but the predecessor of Tom was Karen Sipido. We already had those discussions, because particular people using cell cultures from 300 mouse embryos, and then they had this stock, and they were doing all these experiments from one single stock. So this is the thing. We did studies with Göttinger pigs, And we wanted to, during feeding time, we said, well, we'll feed them. And then we realized, no, then they will become one experimental unit if they all feed from the same source. So during feeding, you have to separate them out. Otherwise, they're a large n equals 1. Well, with 9 gutting and mini pigs, you tear your hairs out if you haven't. But so you really, yeah. But I think it is, most journals now it is.
Can you move the mic across? There.
Hello.
Oh, yes, you first. Go on.
Thank you. My name is Mihaela. I'm from Romania. And I have a question, maybe more questions. How do you feel about classifying heart failure on the basis of ejection fraction, given that it is a measure, or maybe some measurements, but it is a clear cutoff of something that is a spectrum? And it is a lot of research, or scientific community tells us to make the research on the heart failure with the preserved and mid-range and the reduced ejection fraction as groups of different patients, but they are, I don't think they are really different, or the separation is not real.
You've seen a lot more information in my presentation than I did myself, but no, this morning Jolanda van der Velde talked about the preserved, mid-range and reduced ejection fraction. And I heard Scott Solomon give a presentation, I think a year ago, and he said, we defined the mid-range ejection fraction at some point because we wanted to separate the preserved from the reduced and not have the sort of the middle gray area. And now it's in the ESC guidelines. The mid-range ejection fraction patients are a separate entity, and I don't think there's any evidence for that. But it's good if you study concepts that you stratify or you polarize as much as possible to look for differences initially. So, but I cannot give you a cutoff point for ejection fraction.
I don't think it should be given any cutoff points. Okay, but just orientative. But in the end, I think it's misleading to have to categorize patients just on one parameter so strictly and to guide all research on that things.
Yeah, I think it's human nature to make things as simple as possible, but I don't know who said it, but make it as simple as possible, but not simpler than that. And I think what is preserved? Is it above 50 or 55 initially? It's the same with the fractional flow reserve. Initially it was, I think, 0.8. And then the Americans said, no, it needs to be 0.75 because all the interventional cardiologists love to put in, it was 0.75, and then it went to 0.8 because you can put in more stents. So, the cutoff points are very arbitrary, I think. I totally agree.
Yeah, I think you're right. All cutoffs for continuous variables are effectively a compromise for functional use. There's another question here.
Unfortunately, including V less than 0.05.
Yeah. Can we have the microphone there? You've got it. Good.
Thank you. Thank you very much for the very nice talk. I would like more to make a remark than a question. I think that we should see the clinical trials and try to mimic them in terms of primary endpoints in the basic science, because in this way we can evolve and categorize the effects that we see, and probably additionally to the individual points that we should show, we should also include mean and standard deviation as an absolute value so that we could enhance meta-analysis. And I don't know what your opinion is, but doing a review is much more easier if every one of us, even in low impact factor journals, show all of our data.
I hear Professor Hoyes already commenting. I think it's very good for translational research if the lab, for certain experiments, tries to mimic the clinic. I think the other way around would be great too. If in the clinic people would try to use the methodology, in the strict methodology, for example, area at risk, ischemia time, although it's not always possible. But I've had discussions with clinicians that I said, you cannot draw this conclusion based on flow velocity reserve. I said, you need to have flow, and preferably per gram of myocardium. I said, but we cannot measure it. And then I say, don't draw that conclusion, because you're doing it on mediocre data. But it's the best you can do. But so in that sense, I think it's good for translational research if you try the approach and that we apply in the lab clinical measurements to see if it translates, for example, into an improvement in ejection fraction or things like that.
Okay, we've got time for one more if anybody's got one. No? In that case, thanks again, Dirk.